a restaurant. I think it was something like this. And they were ordering things like burgers. Which you could order a choice of burgers, hot dogs, chili, and let's say tuna. The numbers were a little different on the homework, but the same idea. So the question is, how many different orders are possible? Okay, so the trick here is as follows. A typical order might be five burgers and 2 hot dogs, or 3 burgers, 2 hot dogs, 1 chili, and whatever, the rest would be tuna. So the way to think about that is think of the orders as the dividers. So you can have burgers, you could have hot dogs, you could have chili, you could have tuna, right? I don't need this one. Wait a second. So I have 4 different possible orders, right? Which means I have 3 bars, and a typical order might be, for example, 2 burgers, 2 hot dogs, 1 chili, 2, 4, 5, and 2 tunas. So this is a classic stars and bar problem. So we have a total of 7 stars and 3 bars, or a total of 10 positions. I'm going to choose 7 of those positions for the students, or equivalently 3 for the bars. And this would just be 10, 9, 8 over 3, 2, 1. And that solves the problem. One more example to illustrate stars and bars to review the idea for you. Suppose I look at the following. And suppose I require, so I want 5 numbers whose sum is 40. I require that x1 and x3 be greater than or equal to 3, and all xi are positive. So this is really a stars and bars problem as well, positive and integers. Okay. Think of the problem the following way. Suppose I want to distribute 40 identical dollar bills among 5 people. I want person X1 and X3 to get at least $3 bills. Is that so? Who's ringing like that? Is that me or somebody else?
That's you, Professor. We can actually see your notifications.
I'm sorry?
We can see your notification. Just full disclosure.
I'm sorry. Could you say that one more time, please?
We can see your notification.
What notifications?
So you got a text from
text
Tiff Harris. And
oh, really?
Yeah.
How could you see that?
It's because you're on screen share on your iPad.
Oh, it's coming on my iPad.
So you could probably turn on Do Not Disturb, and then.
All right, I'll worry about it later.
Okay.
I didn't realize my iPad was picking up my notifications. Okay, thank you. Okay, so let's get back to the problem. That's interesting. I'll figure that out later and I'll turn it off. Good thing I'm not getting any weird notices. Okay, so the way to handle this problem is give x1 and x3 3 right off the bat. So I'm giving away 6 in total, right? So that means instead of 40 items, I have 34 items, or 34 stars. By giving each of them 3, I'm automatically taking care of that constraint. And since I have 5 x1 through x5, if you think of them as being people, I have 4 bars. So that gives me from 38 items, I want to choose 4 or 34, and that would solve the problem. Okay. So at least I reviewed a couple of stars and bars for you because you guys are too shy to ask questions. Hopefully you'll get less shy as the semester progresses. The last thing I did in our last meeting is I talked about the binomial expansion. And along the way, I used the identity, what was it, that n choose k is equal to n minus 1 choose k minus 1 plus n minus 1 choose k. In fact, I showed you that Pascal's triangle is based on this result. Pascal's triangle is you begin with a 1, then go 1, 1. Begin with a 1, add 1 plus 1, you get 2, and put a 1. Begin with a 1, 1 plus 2 is 3, 2 plus 1 is 3, add a 1. One more. 1, 3 plus 1 is 4, 3 plus 3 is 6, 3 plus 1 is 4, 1. And this row corresponds to the coefficients of x plus y to the 4th power. This row corresponds to the coefficients x plus y to the 3rd power. This one, x plus y to the 2nd power, x plus y to the 1st power, and x plus y to the 0 power. So what this says, if I want to compute, for example,
recording stopped.
What happened to the recording? I must have accidentally hit it.
Could be a memory problem.
It stopped, Professor.
Okay, it should be recording now.
We didn't get a notification.
I'm sorry?
I did not get a notification that it
Oh,
continued.
I did, but it's okay. I think we're good now. Okay. I don't know why that happened. Strange things happen with technology that you always figure out later after the fact. So, for example, if I wanted to compute x plus y to the 5th power, I can get the coefficients pretty easily. 4 plus 1 is 5, 4 plus 4 is 8.
Wait, Professor, wouldn't the middle one over here by the 4s would be 6?
I'm sorry?
Wouldn't the middle one?
Oh, I added wrong, didn't I? Yeah, let's see.
Yeah.
Supposed to be 1, 5, 10, 10, 5, 1. So this would turn out to be just x to the 5th plus 5 x to the 4th y plus 10 x to the 3rd y squared. Notice the pattern. I'm getting the coefficients from Pascal's triangle, and the powers of x decrease by 1, and the powers of y increase by 1 with each term. Plus 5 x to the 4th y plus y to the 5th. Now, this is not the most convenient way of generating these coefficients. For example, if I wanted x plus y to the 87th power, I'd have to do a lot of work on my Pascal's triangle to get it. I do know that it would look something like this: x to the 87th plus some number times x to the 86 y plus some number times x to the 85th y squared, and so on. And suppose I said find the 15th term in this expansion. Well, it turns out there's a trivial way of doing this problem. And by the way, I wanted to observe, how did this identity come in? Well, for example, when I computed the 6, I added this term and this term, right? Which is basically, this is the 3rd term when n is equal to 6 is equal to 5 choose 2 plus 5 choose 3. That's basically how you got it. I think I'm in the wrong row. Well, you can check that later. Okay. So the question is, How do you find the coefficients? Okay. Well, the answer is pretty simple. Suppose I was doing x plus y to the 5th power. That would be x plus y times x plus y 5 times. Now, what will happen in the multiplication? And let's suppose I want to determine the coefficient of x cubed y squared. Suppose I wanted to find this term. Well, when you do the multiplications, there are lots of ways of getting x cubed y cubed. You can get x times y times x. Or you can get an x times y when you're doing the cross multiplications. Or a y times an x times an x. Or you can get a y and an x, a y and an x, and an x, and so on. But notice, if you look at every one of these things, there are 5 positions, and in these 5 positions, how many of them have to be an x? 3. So the total number would be 5, choose 3. So in fact, if you realize that, if I have x plus y to the nth term, and I want to find the coefficient of x to the k, y to the n minus k, its coefficient would just be n choose k. And in fact, this proves the so-called binomial theorem that you all learned in algebra, but we'll write a little differently. The binomial theorem says x plus y to the nth power is equal to, first let me write it the following way. Oh, well, I'll write it out a couple of ways. Okay. It's equal to x to the n plus n choose 1, x to the n minus 1, y, plus n choose 2, x to the minus 2, y squared, and so on. The general term and the last term would just be y to the n. In fact, I can write this more succinctly as follows. I'll write it 2 different ways. Oh, sorry, I forgot the combination. K going from 0 to n. Or if I wanted to, I could write it this way. Remember, n over n minus is the same as n over k, meaning I can start with the y's first. So let me illustrate a typical example, okay? By the way, notice, this is the first term, this is the second term, this is the third term, and so on. So for example, if I wanted to compute 2x plus 3y to the 5th power, and suppose I want to find the 4th term in this expansion. I can find them all, but suppose I wanted to find the 4th term. Firstly, by the way, I think of this as being a plus b to the 5th, where a is 2x and b is 3y. So the 4th term, well, the first term would be a to the 5th. The first term would be 5 choose 1, 8 to the 4th, B. The third term would be 5 choose 2, A cubed B. And fourth term would be 5 choose 3, 8 to the fourth. I'm sorry, this was a 2, wasn't it? Oh, I'm sorry, no, it's adding up to 5, right? Right, there's the 1, 2.
I think the A value is incorrect.
8 to the fifth plus 8 to the fourth B plus A cubed B squared plus 8 to B cubed and so on, okay? So this is the term I've asked you to find. So it's 5 choose 3. A is equal to what? 2x. B is equal to 3y cubed. So this is the fourth term. 5 choose 3 is equal to 10. This is 2 squared times x squared. This is 3 cubed times y cubed. So this term is equal to 10 times 4 times 27 x squared y cubed. This is the coefficient that I want in this problem. Okay? Let me look at another variation on this. Let me just, there's one I want to look at. Need my glasses so I can see. Consider the following problem. I'm purposely taking an even one here. Suppose I look at x squared minus 1 over 2x squared to the 20th, and I want to find the coefficient of x to the 20th in this expansion. Okay, let's see what that means. So any term in this expansion would have would be of the following form: 20 choose k. This is the general term. X to the k. Well, let's say, I'm sorry. Let me write this a little different. If I think of this as being a plus b to the 20th, the general term would be 20 choose k, a to the k, b to the 20 minus k. By the way, if you wanted to instead, you could have equivalently said 20 choose k, b to the k, a to the 20 minus k. This would work as well. You're just interchanging the order of A and B. I'll work with this one. Okay, so 20 choose k. A is equal to x squared. And b is equal to minus 1 over 2x squared to the 20 minus k. Okay, so this is the term I'm looking at. So let's play some games here. Okay, so this is 20 choose k, and now I'm using the laws of exponents. This gives me x to the 2k. I get minus 1 over 2 to the 20 minus k times 1 over x squared to the 20 minus k. Everyone see how I just distributed the exponents? Anybody have any questions? This is called algebra 1. Okay, so let me get all the coefficients together. I get minus 1 over 2 to the 20 minus k. And now I have x to the 2k over x to the 40 minus 2k. Everyone see how I use the laws of exponents? Okay. I have 20 to the k minus 1/2, 20 minus k. And now using the laws of exponents, I get x to the 4k minus 40.
Professor, I kind of
I want to
lost
find
you.
it, okay. Now I want this power to be 20, right? We want the coefficient of x to the 20th. So that means 4k minus 40 must be, what did I say, 20? So 4k is 60. So k is 15. Here's my coefficient. So I have the coefficient, therefore, is 20, choose 15, minus 1/2 to the 20 minus 15. Oops, k is 15, right? So let me just erase that. So this coefficient is equal to 20, choose 15, minus 1/2 to the 5th. That'll give me a minus 20, choose 15, and 2 to the 5th, 2, 4, 8, 16 is 32. Of course, I can now simplify this answer. The problem is now solved. Okay, so that was a trickier problem. So the important thing to remember, the general term is always in the form, oops, sorry. Say x to the k, y to the n minus k, x to the k, y to the n minus k. And in a problem like this, when we had x's, we had to get the appropriate power of x to the 20th. And that's how I manipulated this problem. When you do exercises on the binomial expansion, you'll see it. So now you understand why we call this symbol a binomial coefficient. Because it actually represents the coefficient if you did the binomial expansion. Now, just an added remark. Suppose I wanted to find x plus y plus z to the 20th power. I'm not going to prove this now. And in fact, suppose I want to find the coefficient of the term x to the 4th, y to the 10th, 14, z to the 6th. Suppose I wanted this coefficient. Let me tell you what the answer is, okay? Without proving it. The answer will turn out to be 20, choose 4, choose 10, choose 6. That's called the multinomial coefficient. You can prove it in a similar way to what I just did in today's, in the last 10 minutes, by looking at the, instead of the binomial expansion, you can look at the multinomial expansion. Remember, every single term, when you look at x plus y plus z to the n, in every single term, the power is x to the a, y to the b, z to the c, where a plus b plus c are integers, non-negative integers, they add up to n, just as the binomial expansion. That's a pretty result. I don't want to spend any time on it because it's not probability, but I thought with the binomial expansion, it pays to talk about this a little bit, just for the sake of completeness. Okay, so at this point, we finished all the preliminary material, and now we're going to talk about probability. Make sure the first part of your homework assignment includes the exercises in section 1.6. So I want to talk about basic notions right now. Probability has an interesting history. It started, and by the way, along the way, if you guys have questions, please ask them, okay? I know I'm doing a wonderful job explaining everything, and everything is just sinking right in, and you understand everything totally. But just in case, if you have a question along the way, do ask it.
Professor, I didn't follow you.
I'll let you know in a nice way.
Professor, could we go back like a little bit? You went a little bit too fast for me.
What, on what?
Like if we go back up on the notes.
But particularly what is bothering you?
No, I just couldn't follow the second to last part after what you wrote.
Show me where, okay,
Right there, the red.
here?
Yeah.
Did you understand how I got to this spot?
Yeah.
Okay. So when I got to this spot, this is my power in x, right? Right here.
Yeah.
And the question was, we wanted the power of x to be x to the 20th. We wanted the coefficient of x to the 20th here. Right? And the problem was find the coefficient of x to the 20th in this expansion. We wanted to find the coefficient of that when you multiply it out. So that gave me, when I looked at this expression right here, I knew I wanted the power of x to be 20, so 4k minus 40 had to be 20, and that gave me k was 15. Well, if k is 15, I just have to substitute now in here to get the coefficient. So
I'm just a little bit confused. How do we get 4K?
How did I get 4k? Well, look, this is called algebra now, okay?
Yeah.
What is x to the L over x to the m? Isn't it x to the L minus m?
Oh, yeah.
So look here, there's a 2k here, 40 minus 2k. So if I bring this up, I get 2k minus 40, minus, what was the power? I lost the power. 40 minus 2k. And that's equal to
4K minus 40.
40. That's the law of exponent. Well, if k minus 40 is 20, then k has to be 15. And then I just substituted for k. Let me give you another variation of that, okay? A slight variation. Let's suppose I wanted 2x squared minus 1 over 3x cubed, and I wanted to do this to the 20th power. I'll tell you what the question is after I figure it out. Now, the general term in this expansion, in fact, if we think of this as being a plus b to the 20th, the general term in this expansion is 20, choose k, a to the k times b to the 20 minus k. So in this case, this would turn out to be 20, choose k, 2x squared to the k minus 1 over 3x cubed to the 20 minus k. This would be the general term. Remember, I haven't told you which coefficient I want because I don't know what they turn out to be yet because I didn't work out this problem beforehand. I want to find the coefficient of x to a power that I'll specify in a minute. So I know I'm going to get 20 choose k here. This is 2 to the k. This is x squared to the k. I'm using my laws of exponents. Minus 1/3, 20 minus k, 1 over x cubed to the 20 minus k. So let's rewrite this as 20 choose k, 2 to the k, minus 1 over 3 to the 20 minus k, x to the 2k, and 1 over x to the 60 minus 3k. This is x cubed raised to the power 20 minus k, a power to a power you multiply. Let me just rewrite this. This is x to the 2k over x to the 60 minus 3k. And I could rewrite this term as x to the 5K minus 60. Okay. And now let's suppose I go back to my original problem so I can figure this out. And suppose my question here was, find the coefficient of x to the 15th power. Okay? So that means I want this to be x to the 15th power. That means 5K minus 60 should be 15. 5K should be 75. So K is equal to 15 in this case, coincidentally. Okay. So that means the coefficient, if I wanted to find it, would be 20 choose 15, 2 to the 15th, the minus 20 minus 20 minus K is 5, minus 1 over 3 to the 5th, or the coefficient would be minus 2015, 2 to the 15th, over 3 to the 5th, if I work that out. So it's the same idea. So you'll need to play with this a little bit to get some familiarity with it. Okay. I hope that answers your questions. Play with it, and you'll see how nice it really is. So now we go back to probability. And we want to talk about the basic axioms of probability now. Okay. Well, it turns out that in the 1700s, there was a gambler whose name was a Chevalier de Marais. Chevalier de Marais, I abbreviated his first name. He was a gambler. And what he did was, here's what he asked people to do. He said, toss a die. You know what a die is? It's a single pair. If you have a pair of dice, a single one of them is called a die. And he would give them odds, saying in 10 tosses, how many times a 6 would show up. And it turned out he was winning consistently. So people didn't want to gamble with him any longer. So he said, okay, let's change the rules a little bit. And what he did is proportionally, he changed the number. He went from one die to a pair of dice, and he changed the number of 6s that would appear. And he thought, since he did things proportionally, he thought he would still be winning the same way, but he started losing, and he didn't understand why he was losing. So he went to these two mathematicians at the time, guys by the name of Fermat and Laplace. This again was in the 1700s. And they tried to figure out why he was losing. And they essentially constructed the basic axioms of probability theory. So, and they really didn't use the axioms. The axioms came about later in the early 1900s by the Russian mathematician whose name was Kolmogorov. But they started figuring, let me tell you how they interpreted probability. And then they learned to count a little bit because they needed that in order to figure out probabilities. And they said, okay, instead of talking about a probability, they talked about what we call the relative frequency. So let me talk a little bit about this. And this is not the definition we're going to use, but to give you some intuition. So suppose you toss a fair coin 1,000 times. What could happen? Well, if you do the experiment once, and by the way, I assume when you toss a coin, it can't land on its side. It's always going to be a head or a tail. So let's suppose out of 1,000 times, you get 487 heads, and you get 513 tails. Does that up to 1,000? Yeah, okay. So that means the relative frequency of heads is 487 over 1,000. And the relative frequency of tails is 513 out of 1,000. Now, somebody else might do this, and they might get, for example, 502 heads and 498 tails. So their relative frequencies would be 0.502 and 0.498. Somebody else may get something else. So, but notice a couple of things. Firstly, the relative frequency of heads is always a number between 0 and 1. It's a percentage, right? It was 48.7% the first case, 51.3% in the second case. The relative frequency of a tail is always a number between 0 and 1. How might it be 1? Suppose it's an unfair coin and it was tails on both sides. So there would always be tails if you flip it. Notice in this case, there are only two outcomes, what we call sample points. And the sum of these two relative frequencies must total 1. And notice since there are only two outcomes, one relative frequency is 1 minus the relative frequency of the other. So a relative frequency is essentially the percentage of times something happens. Now, if this were a random experiment, let me talk, what do I mean by random experiment? A random experiment is one that you could repeat essentially in unchanged conditions, which by the way itself is an impossibility. The temperature of the room could change by a 10th of a degree, when maybe that'll affect your outcome. But realistically, think of it of performing some kind of experiment. What do I mean by experiment? An experiment can be tossing a coin. An experiment can be picking a marble out of a whole bag of colored marbles. An experiment might be the lifetime of a light bulb. So I use the word experiment in a very, very general way. And by a random experiment, I mean an experiment which essentially can be repeated in unchanged conditions. Now, if an experiment is random, for example, if I toss this coin 1,000,000 times, we would notice that what should happen here, the relative frequency of heads should approach 50% or 1/2. The relative frequency of tails should approach 1/2 in this case. Suppose I had a bag of balls. Suppose I had 30 red marbles. I had 40 blue marbles, 70, let's say 45, okay? That's 75, and 25 yellow marbles. And these marbles are otherwise indistinguishable. And now let's suppose I blindly stick my hand in this bag and I pull out a marble. Okay. Well, there are a total, by the way, of 100 marbles in here, right? 100. The frequency of getting a red marble, what do you think it's going to be? It'll just be 30 out of 100, right? If this were an idealized experiment and we mix them up really well, or 0.3. The relative frequency of getting a blue marble would be 45 over 100, or 0.45. This is if you repeated this experiment infinitely often. It might happen that if John Smith this experiment and he did this 10 times, maybe he doesn't get 30% of the time a red. But if you repeated this an infinite number of times, this is what should happen. And for the yellow one, similarly, it would be 0.25. So notice, in a sense, a probability, what do we mean by a probability, is the number of times, well, let me say it a little differently. So we have the notion of a relative frequency. By a relative frequency, what happens, what does a relative frequency become as we repeat the experiment n times, and n goes to infinity? That's what I mean by a probability. So while if I took this experiment above with the balls in the bag, if I did it 10 times, maybe I don't get red 30% of the time. I won't get blue 45% of the time. I won't get yellow 25% of the time. But if I did it 1,000,000 times, maybe I would get 0.92, as my relative frequency for heads. Maybe I get 0.511111 for my relative frequency of blue, and so on. So by a probability, what do I really mean? The probability is the limiting relative frequency as n goes to infinity. So if you take an experiment, a random experiment, and repeat it infinitely often, meaning you take the limit as the number of times you perform this experiment, and you repeat it infinitely often, then the relative frequency approaches some fixed number, which we call the probability. So for example, if I took this experiment with, what did I just have? How many in here? 30, 45, and 30 red, 45 blue, and 25 yellow. If I take the relative frequency of red and take the limit, repeat this experiment 1,000,000 times, n times, this would give me the probability of getting a red. Does everybody understand this intuitive argument here? So for example, if I have a deck of cards, a well-mixed deck of cards, 52 cards, what's the probability I would get an ace? Well, how many aces are there in the deck? There are 4 aces. So each time, what do you think the relative frequency of getting an ace is? Anyone?
4/52.
You would think it would be 4 out of 52 on average. If you repeated this experiment many, many times, it would be 4 out of 52. Now, somebody might do this 10 times and get 10 queens. That could happen. It's a rare event, but it could happen. But if he did it infinitely often, as n approaches infinity, this would be 4 out of 52. This is what you would expect to happen. Now, there are problems with this reasoning. So they needed to put this on a firmer foundation, but they wanted to use their intuition as well in formulating certain axioms of probabilities, and that's what we're going to do. So while this argument is pretty good, it makes a lot of sense, and in fact, I'll come back to it in a little bit later in the text. It'll be called the law of large numbers, or the weak law of large numbers. It makes a lot of sense, but it's not axiomatic enough. So we're going to look at this. We're going to take an axiomatic approach. In defining probabilities. So firstly, I have the notion of a random experiment, okay? So I've already defined what I mean by a random experiment. By a random experiment is essentially an experiment that I can perform anytime I want in essentially unchanged conditions. For example, a random experiment might be my tossing a pair of dice and observe the sum of the spots on top. A random experiment might be having 10 children, a family of 10 children, and observe the number of boys that are born in that family. A random experiment might be having a bag of 30 marbles, 15 of which are red and 15 of which are blue, and pick 10 marbles and see how many red you get. So there are lots of different ideas of a random experiment. So there are some terms that we want to talk about. So firstly, we want to define what we call by the sample space. And the symbol I'm going to use for sample space will just be S, capital S. The sample space is the set of all possible outcomes in a random experiment. Okay? By the way, if you think in terms of set theories, we will. The sample space is essentially the universal set. Example. Toss a coin twice. Observe, okay, all outcomes. Well, if I toss a coin twice, what can happen? I can get ahead of my first toss, or a tail on my first toss. My second toss, I can get a head or a tail. So what can happen? I can get ahead of my first and ahead of my second, or I can get ahead of my first, a tail on my second, or I can get a tail on my first, a head on my second, or I can get a tail on my first and a tail on my second. So this would be my sample space in this experiment. Okay? And by the way, sometimes the unique outcomes in my sample space are called sample points. So in general, my sample space consists of these points. It's possible that the sample space is infinite. So for example, the first sample point is this one. It's just a shorthand way of writing it. So I have a sample space, and I have sample points. It may have a finite number of points, it may have an infinite number of points. An event, A, we'll call it E, okay, is any subset of S. So for example, an event might be, let A be the event all heads. Well, in this case, in this example above, all heads, the only way that can happen is H1, H2. Another event could be the number of heads equal to the number of tails. How could that happen? Well, the only way the number of heads can equal the number of tails is if I get one head and one tail. Or that's it, right? Is there any other way? That would be B. So I have the notion of the sample space, which is just S up through S of n, and have events. Okay. So now I want to define, let me look at my notes here. Oh, by the way, I want to remind you, events A and B are said to be disjoint or mutually exclusive if their intersection is the empty set, meaning they can't happen together. Oh, I don't want to forget. Okay, so now let me talk about the three axioms of probability. Okay, so the axioms. Okay, so I want to use the same notation I have. So let S be the sample space. Of some random experiment and let A be any event. Okay, so I have S and I have E. I have A. So A, remember, is just some subset of S. Okay. To each A in S, we define a number, and the number we're going to define is P of A. Guess what? P of A is going to be the probability of A. It's a number. By the way, some books write PR of A. Okay? Just to note that. That satisfies the following conditions. Now remember, we're now defining axiom, but our intuition is based on the notion of relative frequency. The first condition is that this number, P of A, is always a number between 0 and 1. Remember, my goal is to define a probability. My intuition is a relative frequency. We saw a relative frequency was always a percentage between 0 and 1. Okay. Secondly is P of S itself, the probability that something happens, is equal to 1. Remember, if you perform an experiment, something has to happen. Okay. And by the way, sometimes this is called a normalization condition. Normalization. Suppose A1, A2, and so on, there may be an infinite of these, are pairwise, I'll explain what I mean by this in a minute, mutually exclusive events. That means if you take any two of these, any two different ones, when they're different, their intersection is the empty set. Okay, so we have these events. Then the probability of their union is equal to the sum of their probabilities of all possible odds. Now, where did that come from? remember the relative frequency of heads plus the relative frequency of tails. Well, I'm stating this all right, let me just stop here. I'm stating this. Okay. So far I have these two axioms. By the way, notice this could be an infinite union. So it follows immediately from the infinite union. So in particular, if A intersection B is the empty set, the probability of A union B is equal to the probability of A plus the probability of B. Okay. Oops, there goes my glasses. Now, I want to make an observation along the way. I noticed that A, I can write as A union the empty set, right? And notice they have nothing in common. So that means the probability of A, which is equal to the probability of A union the empty set, is equal to the probability of A plus the probability of the empty set, because they're destroying. So I have the following equation. If I subtract, these cancel. So I've just proven the probability of the empty set is 0. So there's one immediate consequence. By the way, sometimes this is called, for a discrete set, the impossible event. Got to be a little bit careful here, because if an event is impossible, its probability is 0. We're going to see later on in the semester, there are events, there are outcomes that are possible, which also have probability 0. That's a little thing we'll talk about later on. Here's another observation. We know that A intersection A complement is the empty set. So let's consider the following. And we also know that, let me put this fact down first. And we also know from the above axiom that A union A complement is everything, is a universal set, is a sample space. So what do we get here? And we know this is equal to 1. Now, since A union A complement is disjoint from the above axiom, this is equal to P of A plus P of A complement. So we've just proven that the probability of the complement is 1 minus the probability of A. That's an interesting result. So for example, if the probability, suppose the probability of rain is 0.7, then the probability it doesn't rain is 1 minus 0.7 or 0.3. Okay. Interesting result. Oh, one more. Where am I? I got to check the time. Okay, I'm good. A non-trivial result. Theorem. Well, we know Let me say it differently. We just proven above, or actually say as an axiom above, that if A intersection B is empty, if they're disjoint, then P of A plus B, I'm sorry, not plus, union B is equal to P of A plus P of B. Now let's generalize. If A intersection B is not equal to the empty set, then, in fact, all right, I can say it this way. P of A union B is equal to P of A plus P of B minus P of A and B. How do I prove this? Okay. So the trick is as follows. Let's suppose this is my universal set, my universe, my sample space. This is A, and this is B. So if I put a number in the circle, that would represent the probability. For example, I'll illustrate in a second. So this would represent the probability of A now, okay? And this region right here would represent the probability of A, of B intersection A complement. That is, I can represent the area in the Venn diagram as the probability. So let's look at this a little bit more closely. And let's observe, I want to do it the way I did it in the book, so I do it a couple of different ways. Let's observe that I could write A union B as follows. I can write it as this region, A union with this region, which is A intersection B. A complement intersection B. Now notice these two sets, their intersection is the empty set. So P of A union B is therefore equal to P of A plus P of A complement intersection B. Okay. What do I want to do now? Now I want you to also notice that B is equal to A intersection B. That is this piece right here, union with A complement intersection B. And these two are disjoint. So I have this result up here, and P of B is equal to P of A intersection B plus P of A complement intersection B. So if I rewrite this expression as P of A complement intersection B equals to P of B minus P of A and B, and then substitute up here, I end up with P of A union B is equal to P of A plus P of B minus P of A intersection B. By the way, this is almost the same formula you had for counting the number of elements in the union of two sets. So I've just proven, let me write a little nicer, that in general, if A and B have elements in common, then this is equal to P of A plus P of B minus P of A intersection B. Notice, by the way, when A intersection B is the empty set, it reduces to the previous case because the probability of the empty set is 0. Okay. How's my time? Okay. Let me consider a simple example of this, how we could use this. Suppose, oh, no, not that. If I say 40% of all students are redheaded, that's another way of saying, if I choose a student at random, the probability he's redheaded is 40%. So suppose I tell you the following, 20% of students take French and math. 10% take only math. No, I'm sorry, that's wrong. I don't want that. 40% take math. 15% take French. So here's what I'm telling you. I'm telling you the probability that a student takes French, F stands for the event a student takes French, is 15%. The probability a student takes math is 40%. The probability to take both is 20%. So I can use, suppose I ask, well, determine the probability they take none of these courses, none, and B, at least one. So notice the probability to take both, what happened here? The probability to take both was, what was that, 20%? 0.2. The probability to take math is 40%. So this has to be also 0.2, only math. And oh, I'm sorry, this can't be. I have to change it. Let me make this number has to be 45%. So this would be then 0.25. So what do I got? 45, 65, so this must be 0.35. So the probability they take none of these, meaning they don't take math and they don't take French, is 0.35. And the probability they take at least one of these, I could use the formula, but notice I can get it from my Venn diagram to be just a complement, which is 0.65. All right, where am I? Do I have enough? Oops, I'm running out of time. Okay, I didn't complete what I wanted to complete in this section, but you can read section 2.1. And meanwhile, you can do some of the exercise there as well. If anything is troubling you, on Wednesday, I'll clear it up. And there's a little bit more I want to add to the section. Okay, anybody have any questions before we sign off? Or let me just let me, hold on a second. Let me just go back to Zoom here. Okay, that's fine. Let me stop the recording now. Hopefully everything is cool. Okay.